Good afternoon, everybody. Welcome to another one of ABYC's Thursday webinars here. I'm Dave Broadbent, ABYC's Education Director, and the other guy on screen is our not so recently retired. It's been almost a year now, but we keep dragging him back here. Ed Sherman is going to be giving us a great presentation today. So I'm going to go through a couple of housekeeping items and some intro slides here, and then I'm going to turn it over to Ed, and we're going to get into some electrical survey. So like I've done every week, a little update on what we're doing here. We're all still working from home, doing the best we can to support you guys. We're working constantly to figure out how to innovate and provide the best products and content we can to help get everyone through these times. It's different, it's weird, it's nothing we've ever experienced. So we're committed to our members. We have our tech department still working hard, answering all calls, anything you need. Membership's working hard to provide the most member benefits they can. In education, we have a bunch of resources, which I'll talk about in a second here. Weekly webinars, we offer the registration to our members first. And as always, let us know any topics you have, and we'll gladly try to incorporate them as the weeks go on. CEUs, so a lot of people ask about getting continuing education units for this. At the end of the video, it'll be the same process as last week. You get a follow-up email tomorrow with a link to answer that one question to get CEUs. If you're watching this on YouTube, the link will pop up at the end of the video. So follow that link, log in, and you'll get your CEUs for that course. Some of our online resources. We do have our standard certification online if you're looking to do a self-paced certification course. Once again, thank you to Active Interest Media, AIM, for putting our fundamental textbook into an online format for teachers to use. So if you know any schools, you can send them to teachboats.org. They can get on our email list of resources, as well as we're offering that fundamental textbook free through August to any marine educators, whether they're using our curriculum or not. So if you know a school who's teaching and struggling with that marine service tech right now, let us know and we can set them up with that. As always, you can self-study and proctor at home with our ProctorU online proctoring. And then our online learning courses. We are doing different sales, adding new courses constantly. Right now we have the free micro courses to go out. Our basic electrical and corrosion mitigation course is on sale through the end of the month, as well as our essentials of outboard service, which are both really, really great courses. Also adapting a little more. I mentioned this last week, and once again, we do have an interactive online electrical certification class starting April 28th. So it's every Tuesday through Thursday, 3 p.m. to 4:30 p.m. Eastern Daylight Time. And it's live guided through with our instructor, Mike Bonacker. It's a really great way to take the course. We've had some great success so far. If you're looking to get electrical cert and have the time, go to our website and you can sign up for that. And lastly, I did talk about a flash sale last week. So we are having the Blue Sea 8100 or 8110 multimeter clamp meter on a flash sale on our website. The manufacturer price is $201.99. We're offering it at $119.99 for our members. So great member benefit. We're going to potentially sell out, so get on there if you're interested. We'll order more if we have to, but it's a great member benefit as well as some of the other topics I discussed here. As always with questions, type your questions in the question box. If we have time, we'll get to them at the end. And I think from there, I'm going to turn it over to Ed. So make it the presenter, Ed, and we'll get going here.
Okay. All right. Can everyone see the opening slide?
Showing up good, Ed.
All right. Good. In my opinion, electrical system surveys should go beyond some of the obvious things. This is one of my absolute favorite pictures from years ago. I got this from a marine surveyor in New Jersey, and this was a boat that he was actually hired to survey for a pre-purchase survey. It's absolutely mind-boggling that someone thought they could sell that and get any real money for it. So that's an example of the obvious. Some of the things I'm going to show you in this presentation won't be quite so obvious. We're going to make several assumptions here. First, the surveyor is not an expert marine electrician. And time is very limited during a typical survey. And you could spend tens of thousands of dollars for equipment, but I'm going to talk about a minimal investment in specialized equipment. And I think the key point, the takeaway from this, is that the surveyor knows when to call in or recommend that a specialist get involved for further inspection at an additional fee. This is, I think, one of the most important aspects of it is being able to recognize when more work may be needed or more research may be needed to get to the key of a potential problem. ABYC, as most people who work with us regularly are quite aware, has recommendations within its E-11 standard regarding wire support and chafe protection. I mean, the basic rule is all wiring needs to be supported at least every 18 inches. And there are a lot of ways to achieve this. Some modern boat builders are actually molding in wire trays that run the whole length of the boat. They're part of the inner hull liner. But other ways will show up in this slide, where we have some examples behind panel boards showing wire support. And it's all neat, tidy. Everything's pretty clearly identified in these pictures, and labeling, which is also a big requirement within our standard. Over and around machinery, metal support clamps are recommended. And this is an important one because we're fearful that wires can drop down on a moving or hot machinery and cause a catastrophic failure. So metal insulated, as shown here, is what we do recommend. It's amazing how many engine rooms I get into where I see nylon tie wraps being used to support cabling. And the problem with that is it work hardens and gets very brittle over time. And there is the risk that they're going to break and the wire will fall down, hit a hot engine or exhaust manifold or a spinning alternator pulley. Chafe protection, lots of options. Grommets being the best. The others shown will get the job done, but they may not be the best in terms of serviceability later on. Wire type and identification is important, often misunderstood. We only recommend stranded wire for either AC or DC insulation. And one of the things I hear all the time, and it's sort of befuddling, is that we do not anywhere in our standards say that tinned wire must be used. And I've actually seen that on survey reports, and the surveyor actually made the statement that, it was an ABYC requirement. That is plain and simply not true. There are tens of thousands of boats, new boats, in service right now, as I speak, that do not have tinned wire. And although tinned wire is a great choice, but there are 50, 60-year-old boats out there wired up with untinned wire that are still providing good service. It's a nice choice. It does help to mitigate corrosion issues, but it is not required by ABYC. Don't let anybody tell you that. As far as the cabling, minimum surface marking of the individual conductors is required, and type and style, and that refers to insulation jacket materials and properties, a voltage rating, wire size, and temperature rating dry are required. I've been on plenty of boats where you don't see that. Those of you who work on European boats may or may not see it, depending upon where the boat came from. To comply with ABYC standards, these are the minimum requirements, and you'll find this on the insulation jacket. We require that all conductors be identified, and there are multiple ways of doing that. A number scheme, as we see on the left-hand picture, is becoming increasingly common as boats end up with more and more wiring. There are so many wires on the boat. I mean, we're looking at numbers that get into the hundreds. The downfall of that is there's no way you're going to know what wire number 510 is unless you have the manual or access to online resources that are going to identify this for you. So that's a very important component there, and it is part of the standard that, you know, that documentation be included. Some builders, the center photo is actually it's a Viking yacht, as I recall, and they put a code on it and identify each wire, and that repeats itself every 10 or 12 inches down the entire length of the conductor. It's probably the best way I've ever seen to identify cabling. A lot of manufacturers will use heat shrink tubing with printed identification on it. That's a great way to do it. Just remember, from the service side, you know, if you have to re-terminate that wire at any point, you may want to relabel it or try and slide the heat shrink up the conductor a little bit so you can get a new terminal on the end. There are lots of alternatives to how one goes about identifying the wire and cable in the boat, is my point here. You know, there's a color coding table in the E-11 Standard that is recommended, but quite frankly, today, there aren't that many people using that recommended color code table for DC conductors. There are just too many wires to deal with, and you don't see it as much as you used to. As long as the builder provides documentation that can help a service tech or the boat owner decode whatever scheme they've used, it's compliant with our standards. Overcurrent protection is vital and often misunderstood. This particular photo comes from a boat that was getting ready to set off on the Transpac race out of California going to Hawaii, and that 1/2-inch copper water pipe is a great fuse. You'll never have to worry about it tripping or blowing. It's one of the scariest things I've ever seen in terms of how to deal with overcurrent protection. But that's real. That wasn't staged. The rules, we talk about this a lot in all of our courseware. The 740 72-inch rule, as I describe it, and basically this is the location for overcurrent protection devices, and these are maximum numbers. The basic rule says 7 inches from the point at which the cable is connected to a source of power. That might work fine on the back of a panel board. You can achieve that pretty easily, but the 40-inch rule comes into play if you're connecting to a source of power other than a battery post. And there are quite a few of those on board a typical boat. That big red dot in the middle that you see is actually represents the battery switch. So that's a remote source of power for sure. And you've got up to 40 inches away from that to get a circuit breaker or a fuse installed. A lot of the builders today are using a combined panel. They're readily available in the marketplace where you've got a battery switch with a circuit breaker right on the same little panel board. That's a great way to comply with a 40-inch rule, and it ends up being a lot less than 40 inches. The key there to remember is that that cable, if you are going to remotely locate the circuit breaker or fuse, has got to be sheathed or otherwise protected. We're trying to minimize the possibility of a chafe occurring that could cause a short circuit. And then there's the 72-inch rule that only is relevant if you're connecting directly to a battery post. You've got up to 72 inches to locate a fuse or circuit breaker. And again, that cable needs to be sheathed or protected, double insulated, if you will. Couple other key points. The starter motor, there is no fuse or circuit breaker located in that wire run, as you can see on the diagram, which comes right from the E-11 Standard. Even though the top says CE 9.11, that's a pretty old picture, but the picture's the same in the new standard. Starter motors are exempt. They do not require fuses or circuit breakers. That said, there's been quite a bit of evolution in starter motor engineering and design since all of this was first created, and I am starting to see circuit breakers on starter motor circuits. And the reason that that's coming to pass is that starter motor current draws are considerably lower than they were 15, 20 years ago. So they can do it if they want. And some builders have embraced it. I think it's a good idea if you can get away with it. I've been on board boats where the starter motors locked engaged, spun up, and created a dead short circuit in that primary cable that runs from the battery to the starter motor. And I can tell you that it's pretty scary when you've got 4-aught cable that's actually catching on fire, and you're in an engine room space trying to figure out how you're going to get this thing shut off. There's so much current flowing that the battery switch won't turn. You can't manually shut off any power. It's terrifying. That only ever happened once, but it stayed in my mind. So it's why I'm a fan of overcurrent protection in starter motor circuits, if it's practical. And the other exception is self-limiting devices. This is another area where a lot of people make mistakes. They don't understand self-limiting. Basically, a self-limiting device is a device that really can't create any more electrical current than it's rated for. Alternators are a pretty good example. An alternator that's rated at, well, we'll just use 100 amps as a simple number to work with. You're going to be hard pressed to get more than 100 amps out of an alternator when it's running under any circumstances. So I see a lot of people putting circuit breakers in alternator outputs cabling, and I will tell you that as long as the size of the cable is appropriate for the amperage involved, that circuit breaker will never blow. It's going for a ride on the boat. It's a complete waste of money. If there were a short circuit, it would be carried by the conductor, and it just plain would never trip. It's a self-limiting device. Another area where we see self-limiting devices is solar panels. Now they can create quite a bit of high voltage, no question about that, but I've yet to find a solar panel that can create more amperage than it's rated at. It's self-limiting in that respect. So it begs the question whether or not you actually should waste money on a circuit breaker for those circuits. With AC, there are some other rules. The 10-foot rule comes into play, and if the location of the main shore power disconnect circuit breaker is in excess of 3 meters, you're going to need, excuse me, an additional circuit breaker. And this gets very real as we see more and more boats with transom-mounted shore power inlets, and the main panel is forward in the boat somewhere. I mean, it's very easy to get to that 10-foot length. What most builders are doing that find themselves in that situation is putting the circuit breaker right next to the shore power inlet, and that works just great. But early on, I ran into quite a few boats as we started migrating towards these transom-mounted shore power inlets, where the distance traveled could be considerable. We don't rely on the dock circuit breaker on the shore power pedestal. We want one on the boat. There's a lot of pretty bad history with dock pedestals. Don't need to get into that for this session, but let's just say we have no trust or faith in those. So we try to put it on the boat to make sure that if there is a high current situation, it'll deal with it. Locked rotor is an issue with motor circuits, and with DC motors, at least most of the DC motors that we use on small boats, they don't offer any thermal protection. You'll see that on bow thruster motors for sure, but not so much with the small, what I call commodity motors, like bilge pump motors and macerator pumps, things like that. We are starting to see it, but I can tell you that it's pretty new. There's thousands of boats in service right now that are not properly protected in the event of a locked rotor. And a locked rotor is just, a wood shard or a self-tapping screw that got down into the bilge somehow, in this case, and the motor kicks on, but it can't turn because there's a screw wedged in there around the impeller. You'll notice this picture. It's a 24-volt motor, and it's supposed to have a 1.5 amp fuse as a max. And I melted this up in about 20 minutes by replacing it with a 5 amp fuse, and it wouldn't blow. No way. I mean, if I had left the power connected, we could have just melted that whole motor. And the reason this happens is that people overfuse them. And it's a simple thing to check. I can tell you that I'm not sure if it's changed, but for years, Rule was sending out this very familiar bilge pump switch with a pre-installed 10 amp fuse in it. Well, that's great if you're trying to protect the wire run from the source of power to the bilge pump. But if that's the only overcurrent protection in the circuit, and there is a locked rotor situation, I can assure you that that 10 amp fuse will never blow, and you run the risk of, starting a fire. What I'm seeing some boat builders do is they will protect the wire run from the panel or a switch like this with an appropriately sized fuse based on the wire gauge used, and they'll have an inline fuse near the pump that is rated at exactly what the motor manufacturer recommends as the maximum fuse size. That works great. That might be a better way to deal with it. It is a better way to deal with the situation. Wire termination is important, and friction type connectors are allowed, but there is a 6-pound pull test. It's a requirement, and you're going to run into a lot of loose connections. I'll talk in a little while about ways that you can find that pretty easily. We require no more than 4 wires on a given stud, and this one they had a little trouble counting. They got it up to 6. I've got some photos that'll show up that are even worse or better examples. The reason is properly fanning out the terminals to allow maximum contact, so that we don't end up with what in effect ends up being a loose connection that will generate heat. It just doesn't have the ampacity. We don't want screw type terminals bearing directly against our stranded cabling. This is a shot of an inverter. Those screws, the tighter you tighten them, the more strands you break in that stranded conductor. The better units are going to have a plate in there that compresses down on the stranded wiring, tightening it up effectively. So something to think about and look for. AC and DC conductors on the back of panel boards need to be separated, and the AC needs to be covered. Now, there are a couple of ways of dealing with this. This particular builder in the photograph you're seeing created this cover, and this is to minimize shock hazard. A great way to do it. We have not specified limitations on material. That one happens to be made out of Lexan. I've seen some made out of wood. There are multiple ways you can comply with the standard. This panel board, we've got DC on the top, AC on the bottom. There's no separation. This is a non-compliant installation at this point in history. What a lot of builders are doing now is they'll have the AC and DC panel boards as 2 separate panels completely, so that you're mitigating the risk of someone getting shocked if they're in there working on it. And that's really the intent of this. Is we do have a standard that states that access to live AC you need to use hand tools to gain access to these live connections, and that's one way to comply with the standard. In this case, you would have to unscrew the cover to gain access to those live terminals. That's why it complies. This panel isn't compliant either because there's an inverter installed, and there's no indication on the panel board anywhere that the boat has an inverter installed, and it did have, I can tell you that. No clue. DC side, switching, overcurrent protection, lots to look at. All of these fuses are here, and there's no this is all live DC connections, and it's in an engine room space. And several things about this annoy me. One is these stick-on paper labels. Yeah, they've identified the cables all right, but those stick-on labels are going to last about 2 months maybe in an engine room space before they start falling off and end up in the bilge. And there's no covering over any of these fuses. And they're high amp fuses. So that tells me there's quite a bit of current involved. It's also pretty heavy gauge cable. The other aspect of this particular installation that's troublesome, although it was a diesel fueled boat, if it were a gasoline fueled boat, some fuses require that they be installed in a prescribed fuse holder with a protective cover to achieve their ignition protection rating. And well, that was totally ignored in this case. Another issue here is in the upper left, you're looking at a diode type battery isolator, and those cooling fins are there for a reason. These things get hot. And the issue here is that it's mounted incorrectly for maximum thermal heat exchange. You would want these fins going vertically if you were trying to achieve maximum cooling potential. Heat rises. The way it's installed right now is some of that heat is going to get trapped between the fins and it won't rise away. So just a small consideration, an easy recommendation that I would make, because these devices, I can tell you, have historically a very high failure rate due to overheating. And anything you can do to help mitigate that as a potential problem is an easy recommendation on a survey report. Same boat. There's another view of that isolator. Battery switches. They all look pretty much the same. Some of them are orange. These happen to be gray. But what's really important is that they have a dual rating, a continuous rating and an intermittent rating. And yet, you can't really tell by looking at the face of the switch. The stud size on the back where the cables are connected is going to be very different depending upon their actual rating. And it's worth trying to discover whether or not these ratings are appropriate, particularly if it's a boat that's been serviced by an owner, because the price differential between a high amp rated and a low amp rated battery switch is fairly significant. And I think we all know what direction the boat owner will probably be inclined to go in, and that is to get the cheapest switch that looks like the one they took out. Well, that could be a dangerous scenario. Again, access to AC components is a concern, and it's something that, you know, it's got to be followed. Here's an example of a boat builder. This is a brand new boat, and that backside of that receptacle, and it is an AC receptacle, was inside a locker in the main salon area where you know people are going to be throwing all manner of equipment. And these are live AC terminals right here that are unprotected. And it's just not a question of if, it's just a question of when we get some sort of an arc fault because a stray beer can happened to rub up against these hot wires. It's potentially dangerous. Again, in surveys, if you're doing older boats, this is an inland thing. If you go up around the Great Lakes, you've got some really nice old boats that are still using a 2-wire AC system, no grounding. Personally, I think that's a really good recommendation that those boats get updated. You know, these are no longer compliant, and I think that's a legitimate recommendation to upgrade the boat to a 3-wire system to help mitigate electrical shock for personnel. Ignition protection is mandated by federal law. ABYC simply mirrors that. It can be achieved either by equipment rating or by proper isolation of equipment. certain bits of equipment that are popular can't be rated for ignition protection. What comes to mind readily is inverters. Xantrex tried to make a ignition protected inverter, and they had one available. It was a 1,000-watt unit for a while, but they had to take it off the market because the failure rate was so high. I'm not aware of an inverter manufacturer today that makes an ignition protection rated device. Battery chargers are another one. Most of them now are rated for ignition protection. But the point is, doesn't mean you can't put it on a gasoline-fueled boat. You just have to think about where you're going to mount it. This is one of a whole series of diagrams in E-11 Standard that will help you to know where you should not mount non-ignition protected equipment. So if you ever have questions about that, you should look at those diagrams because they'll help you out quite a bit. There's a whole series of them: powerboats, sailboats, different configurations. GFCI devices, we certainly require them on weather decks, engine room spaces, galleys, heads. But keep in mind that the GFCIs that we use are not rated for ignition protection. That's one thing. And the other piece is that they have a very high failure rate in marine applications. The GFCIs that we use are the same grade as in your house. And, you know, the marine environment is such that they will eventually corrode in place, if you will, and not function. One of the tools I will recommend surveyors should have is this short test circuit analyzer. You can test GFCIs with this. What other tools? Well, a DVOM, a clamp-on ammeter that has the ability to measure AC leakage current, conductance type battery tester, and at the very least, a pyrometer that can measure temperature. Or today, I recommend getting, you know, a thermal camera. And, you know, they were very expensive. You can get one now that straps onto the back of your iPhone or your Android phone. And they're around $300-400. But what this can help you with is quite incredible and something that you can't, you know, do easily any other way. Just some miscellaneous pictures came from various surveyors around the country of some of the stuff that we see on boats. Loose connections, AC wires routed through this sharp piece of sheet metal. It's going to chafe through and cause a short circuit. Overheated terminals on shore power cords. These are obvious things that you're going to find and should be looking for. Well, the list goes on. I mean, I've got hundreds of pictures like this. These connectors are made for solid wire, not the stranded wire we use. No chafe protection, and that's just a rough hole. Hose clamps. Oh my goodness, holding these wires in place. On this diagram over here, we've got a steering cable or a steering chain that's actually rubbing up against some of the wiring there. It's going to snag it. It's going to chafe it. It's going to create a short circuit at some point in that boat's life. Four cables per stud. Yep, another one, couldn't count it. This diagram over here, that's a hole saw through fiberglass. Once you do that, without a bushing or chafe protection, you've got razor sharp glass surfaces there that are going to cut through that insulation. Guaranteed short circuit. So is the vessel connected to shore power? Even if unplugged, you could have an inverter asleep that you're going to knock out. Make sure that all the power is off. Assume that a problem exists and make no assumptions about wire color coding and a circuit's function. Some tests with the DVOM. There's a whole list of things that I would go through as part of a survey. You may not want to as a marine surveyor, but you may get suspicious about the boat and suggest, okay, you need to get a marine electrician down here. I found some things that are a little bit shocking to me. We need to look into your boat a little further. And these are some of the tests that should be performed, in my opinion, to make a determination about the quality of that electrical system. Again, the ideal shore test is one of the quickest, easiest tools you're ever going to use. It can tell you things that we don't have time to discuss today, but I can tell you that, you know, in your electrical certification course, if those of you who are considering that, it's a tool you'd learn about. It's one of those 3 LED testers on steroids. It's going to show you all kinds of things that you simply can't find any other way. The barometer, that, and you've got to be careful if you're going to get into thermal imaging. This particular boat had a legitimate problem, but notice how bright that connection is. That's an issue, but not really. You need to look at the temperatures and make sure you see what the variation is. I used to use a 25-degree Fahrenheit temperature spread as a clue that there's a problem. If the temperature at the bright point is 25 degrees Fahrenheit or more than the norm down here, there's a probable issue. Here's a good example of it. That was just taken under my desk where all of the little mini transformers are. It looks horrible on the thermal imager, but guess what? It's only 20 or so degrees warmer than the surrounding area. It's not that big a deal. I mean, transformers do create some heat. AC leakage test. I think you've probably all heard about in-water shock deaths. And here's a dedicated AC leakage clamp that you can't buy this particular one anymore, but it does give you that leakage information. Quite involved as far as knowing some of the other things that it can tell you. Some of the causes are outlined here. Common causes, neutral to ground connections on board the boat. It's a surefire clue that a residential electrician has been working on the boat or old appliances. Old battery chargers, water heaters, other common sources. So there's the link on the back of an electric range that was installed on a boat. That means every time you use that stove, you're going to have AC ground faults. That's it. I think we've got a little time for a few questions.
Yeah, we do, Ed. First, as we've done with all of these, we're giving away a prize to one lucky participant here. So with that, I'm going to launch a quick poll question from Ed's presentation, give you guys about 30 seconds while some of these questions come in for you to answer it. And so you'll see the little poll section, answer it on the screen, and we'll be good. So I'll give you 30 seconds for that. I'll launch that now. right, so we got a few, I'll close this out. We got a few minutes for some questions. The correct answer was 5 amps there. So for those of you who selected 5, I'll go back and we'll pull a lucky winner out of that. So Ed, just to start getting into some of these questions for you, let's see. Start here. If a typical 48 bank let me start over. If a typical 48 volt bank may be at a closer to 54 volts when a float doses fall under low voltage, as far as an ABYC standards are concerned. So does basically a 48 volt bank charging at 54 volts, is that considered low voltage under ABYC standards?
Yeah, that's a good question. All of our standards where we specify voltage values are contemplating nominal values. And so guess what? 48 volts is the nominal value. It's just below the 50 volt threshold. You know, a 12 volt system is really running at more than 12 volts all the time. It's the same thing, just amplified a little because the nominal voltage is higher.
All right. So our next question is, what is the danger associated with boats on the hard connected to shore power?
The risk of there not being a proper ground at whatever plug they're plugged into, you know, the receptacle box that's wire tied to a chain link fence is very high, and it's a huge risk. There's no good ground to carry any fault current that may exist back to a source and trip a breaker, cutting the power off to the boat.
All right. Would you suggest replacing solid wire found on a 120 volt AC system in older boats during a survey?
That's a good question, and it's a tough one to answer. You know, the old boat thing is difficult because you're going to run into an owner that says, you know, this has been working great for 50 years. Why should I listen to you and change it? And that's a tough question to to answer. You run into it up in the Great Lakes a lot because there are a ton of really pristine older boats that were built before the standards even existed in some cases. I would say that the answer is I would recommend it. And the only time I would defer from that is if the boat is truly a classic boat and we've got a scenario where they're trying to maintain it in its original condition as manufactured. And that gets into a whole different realm of surveying, in my opinion. When you're looking at genuine antique boats, it's not a great answer, but it's the best answer I can give you. I think it depends on where the boat's going to end up and what the use is going to be.
All right. Get you another one here. Does separation of AC and DC conductors also apply to enclosed wire runs? Looked at a boat that had both in an enclosed plastic wire run.
Yeah, that's actually pretty common. And the way we get around that is the AC, as long as it's genuine boat cable, it's already double insulated, and that outer jacket over the 3 or 4 wire AC conductors constitutes acceptable separation. It's not the best way to do it, but it's the most common way you're going to see it. I mean, in commercial applications, you're going to want AC wire runs and DC wire runs in separate conduits. That's just not realistic in the recreational world.
All right. We got about 3 or 4 minutes, Ed. So if you got a quick answer to this one, we'll have time for one more. But can Ed discuss new remote remote electronic battery switches?
We're referring to wireless, I believe. And if that is the case, we really don't have any standards in place yet addressing wireless situations. And it is something that I hope the electrical PTC group will entertain as we move forward, because it's going to become more prevalent.
All right. On a through-hole fitting without a dedicated screw, how do you connect the wire to the bonding system? Is a hose clamp acceptable?
Well, we see it all the time, and my answer to that is sure. You don't have a whole lot of choices available to you other than a clamp of some type. And as long as the connection is solid and it's not covered with corrosion, I don't see where you have many choices under the circumstances.
All right. Get you one more, and then we'll have to close out, I think. You mentioned the 6-pound pull test for connectors. Would you recommend fixed fittings instead? How does one test the 6-pound pull test?
Well, the way I've done it in the past is with a little Zebco fish scale that I had laying around, and put a hook end on it and hook it onto the terminal and pull on it. And I will tell you that, and I did it purely to get a feel for what 6 pounds feels like. Trust me when I tell you, it's a lot more than you think it is. If they're loose, you're going to know. They'll literally fall off. The 6-pound pull test is quite significant, actually. Compare the feel for when you push a brand new terminal on versus one that's been on and off 5 or 10 times, and you eventually develop a feel for it that's pretty easy to identify. But use a fish scale if you really want to go crazy with it.
All right, I'm going to jump on screen with you here, Ed. We have another PTC meeting that's jumping on after this, so we got to finish in pretty timely manner here. Ed, thanks for coming off the bench out of your seclusion there, out of retirement, and answering some questions for people here and giving this presentation. If you didn't get your question answered, send me an email. Mike Boddicker will also be able to answer some of those. So we're continuing to do that. Next week, our tech department will be presenting on some of the technical tools and some of the things going on over there. So it'll be pretty interesting stuff if you want to learn a little bit more about the committees and whatnot. So stay tuned for that intro or invite. Lastly, CEUs. I'm not sure where Matt's going to put it on the screen today, but if you're watching this on YouTube, the CEU link will pop up on the screen around now. So click that. You'll get CEUs for it. And once again, thanks, Ed. Thanks, everyone, for participating, and we'll see you next Thursday.
Okay. Bye, all.